Good morning, everyone. So today is the last lecture about materials and systems. We'll speak about steel. This will also be probably helpful for your flipbook section assignments. I don't remember how many of your case studies have actually steel involved, but a few should have at least some choice or something that involves steel. Well, in this case, I'm recommending again the Steel Construction Manual. This is full of resources, and especially the first part, starting from page 8. There are about 60, 70 pages with a lot of images, but they talk about the history of iron and steel. So I would say that that part is rather important, and also the appendices at the end, that they show a lot of projects which could be useful references. The book on the right is, that's a translation of an Italian book, and it's very interesting because it focuses on the city of Chicago. And it's a city full of inventions. A lot of technology happened there, especially in the 19th century. So the development of a rich and very wide train network, the invention of the standards for the current trains, which were invented by Mr. Pullman, who also invented the bus, and steel and the birth of the skyscraper, Louis Sullivan and then Mies van der Rohe, a lot of other things, time precision. There are a few curiosities that could be interesting. So it's a book that you read, on your own, just out of curiosity. So what we'll cover today is, again, the same stuff, material basics, but we'll speak a bit more about the steel manufacturing and properties, because that's a bit more important than the basics themselves. Different types of connections and the way to get pieces cut to size, cutting, welding and bolting, they're very important. And then there are 3 systems I'd like to speak about. So it's residential steel framing. It's actually the same as what you've seen last week. So it's about the light frame just done out of steel. You'll see they are very similar. There are some differences I'll try to highlight for you. Then steel concrete floor, so we'll speak about Bondek. And secondary steel framing, so purlins and girts to make cladding, panelized cladding. So that's it. And after the break, a few slides about steel architecture, generally from the period of the Industrial Revolution until Mies van der Rohe and minimalism. There are recent developments. We could speak about Gehry and digital fabrications, but I don't want to go into that. There would be other subjects that speak about that, especially at the master. That would be too complicated. So we'll stop at the period of the modern movement. How is the microphone? Is that all right? Yes? Good. Steel manufacturing. We already see here an image about hot rolling, but let's talk about the material itself first. Well, so what happens? This is like like concrete. We have some basic material. So it's a product of mining and refining iron ore. So that's where it comes from. And the real difference between iron and different types of iron and steel, the one we use for construction, is the percentage of carbon in the mix. So you see here, wrought iron, that's the purest you can get. You see the percentage of iron is smaller than 0.02%, and cast iron is higher than 1.8 and generally ranges between 1.8 and 4%. Steel sits in between 0.4 to 1.7. And according to the percentage of carbon, the quantity of carbon in the mix, you can actually get different properties. One of the most important ones is weldability, so the possibility to weld different pieces. So that's what happened. Iron, the chemical, you see the symbol of iron is Fe, comes from the Latin ferrum, all right? And look at this. To determine the properties, generally you could say, why don't I add just the maximum percentage I can of carbon so that I get a very hard material, but at the same time you increase the possibility of the material to snap. It becomes very brittle and almost impossible to weld. So that's why in the 19th century most of the buildings done out of steel were done with rivets, because it was difficult to weld them because they used either wrought iron or cast iron. So here you see what happens by changing the percentage. So what type of, let's say, what type of characteristics you get out of that material. And I'd like to speak about a little bit all of those, just very briefly. You know the Eiffel Tower? If you've been to Paris, you see that that's out of, it's not steel, kind of, it's a wrought iron. So you'll see a lot of rivets because the connections were done in that way. It's very easy to work, so you can get a lot of different shapes, so it's very good for ornamental uses, but it's very difficult to weld, and also it's very difficult to product. So to manufacture, the point that you want to standardize this and bring it into the world of construction means that you have the need to be able to produce many pieces in a fast way. That wouldn't happen with wrought iron. So you do it, for very special occasions, and that would happen in that past. So it's not something that you can produce fast. It's very expensive. It would be too expensive. Cast iron behaves in a very similar way, even having the opposite characteristics, so too much carbon in the mix. So you see here again rivets. Very interesting that you see these masonry arches, and then they sit on these concrete pods. This white flange beam is actually, it's a kind of lost formwork for those, concrete pods. And then that's connected with these rivets and this plate to another beam. So you see how easy it is to shape this type of steel in different forms, or the forms you want. But again, no possibility to weld. Here we're talking about a project that I just picked from the Steel Construction Manual, so of the 19th century. Very interesting project. What about the properties? Here we've got something interesting. We know that, for instance, masonry, stones, concrete, they generally perform very well under compression forces and very bad in tension. Actually, we could almost say they don't resist to tensional forces. Well, in this case, we've got an isotropic material. So the same behavior in compression and tension, exactly the same. But we've also got a ductile material. What does it mean? If we look at this diagram here, look at this plastic flow. It means that the material has got an elastic phase. We apply the load, we get a deformation. We remove the load, the material goes back to the initial shape, elastic. We apply that further load, the material can't stand that, so it goes into a plastic phase. We get, as you see here, there is a point, which is this one, in which there is a permanent, non-reversible deformation. Well, in this phase, steel is still able to resist a lot. So it can still go, it tends to agonize, but it tells us, there is a warning telling us, I'm almost there to the fracture point, but I'm still able to resist, and I will keep this shape because I'm in a plastic phase. I won't go back to the initial phase. You recognize this because you see there is a proportion, a linear, there is a proportion in the development of this elastic phase, and then it changes suddenly, and it's more difficult, so there is not a linear proportion in the ratio between stress and deformation. But that's very important. So we'll say that both in tension and compression, that would be the behavior, and is a ductile behavior because of this plastic phase we see here. Oh, all right, so Milcell, that's the material we use nowadays, and we use it for a few things. I already mentioned that it's a ductile material, but that also refers to cast iron and wrought iron, so that refers to all these type of metals. Weldability, so look at this. When we have less than 0.5% of carbon, we can weld it easily. So that's really what we want. And low cost compared to strength ratio, that's why that? Because it's very easy to manufacture. So this means that we can produce really many standard pieces, and it won't cost as cast iron would. Availability in sections and plates, so it means, again, we can shape it in very different forms. And what are the advantages? High strength, both tension and compression. Strength, the ratio between strength and weight is very good. So it's generally lightweight, but it can resist to very high forces, both in compression and tension. It's stiff, and it doesn't shrink. So creep and shrinkage actually means the same thing. That's important because you don't have to consider that during design, but it can still expand due to thermal expansion. So if you heat it up, then it would tend to expand. So you will still need to consider control joints. Kind of easy to connect rivets, bolts, can be welded. So there are different possibilities to connect pieces together. And there are also disadvantages. You have seen that concrete and masonry, even timber, they work well both as structural elements but also for cladding. In this case, steel needs to be protected because it tends to rust. All right? So we need to protect it from weather agents, or we need to treat it. So just steel as it is cannot perform as a structural element and at the same time for cladding. You can't do that because it's prone to corrosion, so it tends to rust. Also, fire is an issue. So generally, you remember when we spoke about the first patents related to concrete, we mentioned that the tentative was to protect steel from fire. So that the idea to pour concrete over steel was that. And that's one of the poor parts of steel. Yeah, what about steel making? So we have already mentioned, you see here on the left, you see iron ore, we mentioned that. You connect it, you just melt it together with limestone and coal. And now there are two different things. So in the blast furnace, we produce pig iron that then is ready to go into this oxygen furnace. I'll show you all of them individually so that we produce these hot rolled by extrusion slabs. We also get some scrap pieces of steels we want to recycle. So in that case, they start from here and they would go to the electric arc furnace. And then the same process, hot rolling, and we get slabs, or very thin slabs. So this is the blast furnace. Don't know if that's interesting or not, but you just need to know from this slide that we go high to these 1,400 degrees Celsius and we reduce iron to a liquid. So that's what happens. Once we have this liquid mix, then we are ready to process it. That is called pig iron, and what we do, actually this is the type of reaction. So we heat it with coke, so the coal you saw before. So we try to, we separate the oxygen. So this is the original. We've got 2 parts of iron, Fe ferrum iron, and 3 parts of oxygen. We separate it with this heating process, and that's the result. So the pig iron we get is just this ferrum, this iron without the oxygen. After that, I know maybe it doesn't make much sense, but it's just a process of separation of oxygens and iron. Then we need to further reduce the percentage of carbon, and what we do, there is a lance, an oxygen lance, just goes into this liquid mix and it blows oxygen. So that's what happened. This is the lance, and it blows oxygen in, and that's again to further reduce the percentage of carbon. There is an alternative process that, as I said before, when you get scrap steel you want to recycle. There is a very similar process that again heats that up and then makes it a liquid mix, and then it goes again into the oxygen. It's again oxygenated to reduce the percentage of carbon. Before going to the final phase, which is hot rolling, it's like concrete. We can add further, additives to, for instance, like manganese. So manganese is helpful, like to increase the weldability of the material. So there are some extra products we can add to the mix, so that to make it more suitable to our needs. So that happens at this stage, before going to the hot rolling, which is this one. So here is our mix, and the temperature is about 1,600 degrees. So what happens, you see there is this mold. This mold, there is a detail here, so there are 4 plates which are water cooled. So we try to reduce the temperature while extruding the steel, because we want to get a specific shape, generally a slab or a thin slab, the one you see here at the bottom. Then there is further cooling while you pass it through these rollers, several types of rollers, and then there is an oxygen cut. So there is this moment where we cut it to size, and we get these slabs, and there is just the cooling bed. So they stay there until they are completely cold. All right? So that's the process to get the right shapes we want. And then we can make further refinements. But considering that at this stage it's a little bit like concrete, isn't it? So we can more or less get all the shapes we want. So why don't we shape it in order to work properly, in order to work well under specific load conditions? So for instance, we know that generally tensional stresses tend to be higher in the top and bottom parts of beams, and the web is generally something that we can make lighter. So why don't we shape it, for instance, in this way? Or we can use maybe some circular hollow profiles, again, to reduce the amount of material, but still keeping it a very strong product. So what we can do is a family of products we use. And you remember the book I suggested you 1 or 2 weeks ago, this Allen, Fundamentals of Building Construction. There are a few very nice schemes on how to do hot rolling. And for instance, here you see when you want to get that wide flange shape, look at the shape of the roller. All right? So that's the way to get that. And I can show you in another slide that this happens at least in 3 phases. So there is it's even like the same happens when you have a CNC. First, there is always a first rough pass. So you tend to get this shape with these 3 rollers, just the first rough pass. Then there is the edger, just a refinement of the edges, and then the finisher. So in these 3 steps, I'm able to get that type of product. You see here the image, the corresponding image to that diagram. And what we can also do, we can get hollow profiles. To get hollow profiles, here you see there is this circular pipe. We already have these very thin sheets that we can just, there is a curve so that we bend them together, and then there is a meeting point, and then welding happens so that we get a circular hollow profile, but still through hot rolling. So this is a hot process, not cold. There is also, we'll see later, there is also another way to cold form steel. So you see here the curve, it bends, and then when the 2 extremities touch, there is welding, so that we get this profile. That's also very helpful to reduce the the weight, the overall self-weight of the material, but still preserving high strength capabilities. So what are the products? As I said, there are families. Unfortunately, there is nothing to understand and learn here. It's mainly about memorizing things, because these are commercial products, and somehow you will remember them because you will use them, they're commonly used in the profession. So somehow you will get to the point to which you remember most of them. Just bear in mind these wide flange beams are the standard sections, and in some cases we'll use these hollow sections. Most of the times we use the hollow section when we get compression forces, all right? And this type of wide flange beams or I-beams, they're used when we want to resist to bending moments, all right? And they're not really subject to compression, like a joist, okay? Just a conventional beam. In these other cases, there are also some hangers or cables or other occasions in which we really need the full solid section. Generally, they're very small compared to the others, and this is the family here at the bottom. But just a few of them, we really need to remember them. And most of the times we also put this type of things in the exam. So just to recognize some different types of beams. For instance, the universal beam, UB, always remember the name, the label, and also how it looks like. So you see here we've got these two flanges and there is a fillet with the web. We will see later also a welded profile where you won't recognize this fillet because we will have three elements which are welded together. So this is one of the ways to recognize this universal beam because of this fillet and also because of the height of the web. Because again, it has to resist to bending moment, so it's very hard. We've got the corresponding universal column. Of course, the cross-section changes. So you see, it's not so high. And that's the way to recognize the universal column. And in other cases, maybe there is an aesthetic intention and structure is not all every time. So what we want to achieve maybe is, we want to attach something onto that surface. So we need that clean and flat surface. So we have this parallel flange channel. So these are profiles that can be used, according to design needs. All right? There are several families of that. Also, corners with equal angles or unequal angles. That's just up to you to browse the catalog and find what satisfies your needs. All right? These are the most common. So I ask you to remember and memorize at least these 4 or 5 types. What about cold forming? Now let's continue from the previous phase of hot forming. We get thin sheets or slabs. We can still perform a few operations on them, and one is folding, bending, the other one is corrugating, and the third one is curling. So by curling we get tubes or pipes, and by folding we get, for instance, this Z-shaped purlin. You see here? This is by folding, and we can corrugate sheets, for instance, for bondage or cladding applications. So these are the type of things we can do, and these are cold formed, so they are not heated up. All right, they're already in shape. Out of that, again, a few standards. Just please memorize a couple of them. Circular hollow sections, CHS. And of course we've got the square one. You see that because of folding, that's the type of fillet again we get in the profile. You remember that before with the hot form one, the profile was sharp at the corners, not in the web but at the corners. Rectangular, and yes, here already you see that there is the parallel flange but the cold formed one. So you see the difference. So because of folding, you see that this one is not straight, there is a little bit of fillet. So that's the way to recognize how similar profiles which perform similar tasks can actually be shaped slightly different. So you will be able to recognize cold form and hot form by means of that. They are generally, these ones are generally weaker. So most of the times this is lightweight but also a bit weaker. The hot formed ones tend to be stronger, all right? Because these have to be obtained using very thin sheets. So the cross-section is slightly different. Other fabrication techniques. So we need to cut the steel to size. So most of the times we can use a few techniques. Or maybe we would like to shape it in another way, such as these castellated beams. So we can use cold sawing, oxycut, or hole drilling, so we can, puncture. We can drill through very thin sheets, generally up to 25 mil. And we can also use this very nice technique, submerged arc welding. That's used to combine together different sheets and make very large wide flange beams. So it's to make extra large and customized elements starting from the basic ones. So these are the 4 fabrication techniques we still need to look at to get all the profiles. Cutting. So this is rather self-explanatory. So what you get is this bend saw. So it's like sawing timber, just in a bit more sophisticated way. So the speed of this bend saw matters, depending on the type of steel you want to cut. And then also, just for safety reasons, you see these yellow clamps? So the profile is actually clamped, not to move. And then you just cut it. Most of the times this is CNC control, so there is a machine that does that. You won't do that manually, all right? But it's actually just sewing. OxyCAD is more interesting because what you've got is, there is look at this gun here. There is a stream of oxygen gas, and there are also some small flames that just preheat the steel to the temperature that is suitable for cutting. So that's, you can realize a very, a very clean cut, and you can also do it on site. But again, most of the times you tend to do it off site if you can. All right, and again, in this case, you see here in the slide from 6 to 300 mil. So it's a very flexible technique to cut steel in a very precise way. Look at this one. This is OxyCAD, but this is performed off-site. So it's CNC controlled to get these castellated beams. All right? Hole punching, what happens here? It's like, the first could be, like drilling, or again, there could be an OxyCAD that performs holes, or punching. So these are the type of operations you can do, and generally you get holes, slots, or very simple shapes. More recently, there is a laser cutting technique that can be used. You have probably been exposed to the Fab Lab already here at the University of Melbourne, and you see that generally what you can do, you can cut boxboard, cardboard, plywood, probably up to 4 or 5 mil. Well, there are also other sophisticated versions of the same machine that allow you to cut steel. For instance, there is one in engineering, at the Department of Engineering, they can laser cut steel. And you can imagine that whatever file you submit, whatever shape you want to cut or hedge on the material, you'll be able to do it. So in terms of precision and automation, you will get there. And generally, for shading devices, this is very helpful. You can get all the shapes you want. Welding. Well, in this case, what happens, we have two pieces of the same material, steel. We use a filler to connect them together. So that's the principle of welding. So there is an extra material that acts as a filler and connects them together. And what happens is that the final result is a material which is as strong as the two separate parts. So it really behaves like a single piece, generally. Why we do that? First, because maybe we want to fabricate members and components. Let's think about wide flange beams. We want to realize a very big one, like that. We won't do that through hot rolling because that's too costly, too expensive. So what we do, we take thin sheets of steel and we weld them together. So that's the way to realize those types of products. In other cases, we want to connect the elements together. We would like to connect a column with a beam, and we could weld them together. So that's another possibility. And you need to remember that there are two different types. So there is the fillet weld and the butt weld. In this case, the fillet weld, again, it's self-explanatory. So you get a T-junction. So most of the times is to connect elements in perpendicular directions. So you get a T-junction and you generate this fillet. So this is the weld face here, all right? So very economical. In the other case, the butt welds are generally used when you don't have a T-junction, but you have coplanar surfaces. So you see these two elements, they sit on the same plane. So what you do, you need to prepare the face first. All right, this fusion face needs to be, cut to get these bevel angles so that you can use the filler and connect the two parts together. This is a very strong type of welding. Remember, fillet welds, T-junctions, and butt welds for coplanar elements. The first one is weaker, the second one is stronger. It should be pretty easy to remember that. In terms of economical considerations, we tend to avoid to do welding on site, even if it happens, and you see that pretty often. But look at the type of equipment you need. So this is the type of equipment, and also you need skilled labor. It's much easier to do that off-site and do that through CNC machines. So you tend to avoid the use of skilled people to do that because, again, it's very expensive and you still get a higher precision by using machines. Look at this one. Look at this profile here. These very wide flange beams. So look at this. There are 3 thin sheets which are connected together by means of welding. So that's the way to realize that. There is no hot rolling process to do that. You could do it, but it would be incredibly expensive. So what you do is that, you get this, look at this one. This is the granular flux, and you physically submerge this arc, and you get this welding. So this is completely automated and precise. And by means of this process, you can realize, whatever profile you need. So just design it, and whatever scale you're looking at, you can make your customized piece. And this is not a recent picture. I mean, this is about, we are talking, probably we are in the 50s. And again, you'll find it in Fundamentals of Building Construction. It's taken from there. So just to show you that this process was already automated probably 60, 70 years ago. And look at the size of the element we're talking about. Again, we get a few standards out of it. Welded beams, they look very similar to the previous ones, but what's the difference? There is no fillet here. We clearly see there are 3 elements and there is a web. So you see the separation between that. So when someone asks you about the difference in standards, you should recognize them by means of that. And again, I'm reiterating this because we tend to give these type of questions at exam, so I want you to know that. Welded columns, again, is a matter of height. So I'll go fast on that. And then bolting. This is a very interesting type of connection because it's widely used and it's probably the most common. What happens with bolting is, you've all seen a bolt, so you know that there is a shaft and then especially there is a head, and on the other side you place a nut, and these 2 elements together, head and nut, they clamp other pieces. So you see all these pieces are clamped by means of bolts, so that's what they are. Look at this. This is the bolt shaft. This is the first plate, the first sheet, the second one, and then we've got a head and then a nut on the other side. Then there is a thread, so we can actually tie the nut in order for the 2 plates to be connected together. But when we've got normal forces, that works very well, so they won't be pulled apart. But when we have horizontal forces, so that there is shear involved, that is not the ideal situation for the bolt. So what happens? In that case, a common solution is that you insert a 3rd plate so that you clamp first the plates and then you place the bolt. So to try to reduce, to contrast shear forces. Okay, shear is always this type of movement. It's the mutual friction of elements. All right? In terms of tightening, you know very well, you probably played also, with IKEA furniture type of thing. You never know exactly how strong you should tie elements together, even screws. Well, in this case, we could say that we have at least 2 types of tightening methods. There's snug tightening, so that the point is that they are tight enough to be in contact. So the two surfaces touch, but there is still a little bit of slippage allowed, all right? So that's called dowel action. In the second case, we have got the full tensioning. So you just tighten, you just tension the elements to the full extent, and you can also use some other tools to calculate the amount of torque. So you can also apply a specific amount of torque, all right? And what type of bolts we use to do that? Well, with the commercial bolts, these ones, they're not identified by any sign, only the M that stands for metric. And in this case, what happens is that you can just use the snug tightening, okay? Not the full tensioning. If you want full tensioning, then you need to use these high strength bolts. You see, they are identified by these radial lines, and again there is this M that stands for metric. Here you see there is another slide just to synthesize that with these ones the snug tight method can be used, and with the high strength bolts you can use both tightening methods, right? Just remember that. I forgot to mention, but I think it's obvious that generally you place also washers inside, and the thread can be full or just half. Generally this is much cheaper. And now I think we spoke about this slippage, and we need to mention that we can actually make two different types of connections. We can make several types of connections, but a main, very rough difference is between rigid and flexible. So rigid is a node that is able to transfer all the forces between elements. So what happens? We transfer compression, tension forces, we transfer bending moment. Flexible joints generally do not transfer bending moments in an appropriate way. And why that? Because look at this joint here. What happens in space? We've got 3 degrees of freedoms in terms of translation and 3 degrees of freedoms in terms of rotations. So one element, whatever object in space, is able to translate on the X, Y, and Z axis, but also able to rotate about the X, Y, and Z axis. When we weld two elements together, that's a fixed connection, it's rigid. So if it's not able to rotate, bending moment is transmitted to the next one. When we have bolts, generally one axis is still, released. It's not fixed. It's not constrained, and therefore the element is able to rotate slightly about the axis. So we can't talk about a rigid connection. And in that case, the solution is that we need to brace the structure so that we can actually control lateral stability. With a rigid connection, there is a little bit of that is taken in account by the joint. So that's the main thing. Look at these two diagrams. This one on the left and the one on the right. These kind of circles, they identify the release of the joint. So they identify that the joint is flexible. So you see this is just a symbol, a convention to identify that there is an hinge. So this circle means that it can slightly rotate, and therefore bending moment is not transmitted. It's not necessarily a disadvantage or an advantage. In most of the cases, we would like to have a structure that doesn't transfer bending moment to the external one. So it might depend on the cases. There is a huge difference between multi-story houses and skyscrapers in residential houses. So that depends on that. Just bear in mind you need two braces in the case of these flexible connections. And most of the times when we use bolts, the connections are flexible, apart from a few cases. And I've just, pasted here a few details for you, and also the same for rigid connections, which it can be bolted, but generally done with these plates that are able to transfer bending moment in all the locations, and in other cases we weld it. But you also need to take care about detailing for bolts. Most of the times what we do is that we draw the center lines of the shaft in the drawings. So we have these small dots and we identify the position of the bolt. But we don't consider the actual size, and there are situations in which we can't even place the bolt, the one on the top, and other situations in which we cannot tie the bolt, such as this one in the bottom, you see here. So these are not, these are not secondary things, so it's very important that you are able to detail these things properly. So when you get these very sharp angles and connections, it's important that the detail is done properly, not to get in this type of troubles. We also have elements to connect steel to other materials, for instance, concrete and masonry. Masonry, generally, they are anchors for connecting these things to the grounds. I'm not really going into details, but what happens is generally, here you have concrete or masonry, so you just drill a pilot hole, and then also you drill the steel plate, and you can just screw in this element. In other cases, you can have this expansion bolt. So again, it's pretty self-explanatory. After the pilot hole is drilled, you place this cage that once the bolt is in, it tends to expand so that it's fixed and you can't take it out. And what happens with the chemical setting is that drill the pilot hole, then you place the product in, and then there is friction while you are, tightening the bolt, and this friction heats up the chemical product that tends to react and expands, and then again you create a fixed, just a single material. This is another type of thing that is rather interesting. So this is stud welding. What happens when you get a plate like that and you want to attach another angular element like that? You need a thread, you need something to attach on it, all right? Well, there is a specific tool, this gun, that is able to weld a thread and rod onto a steel plate. So you get your steel plate nice and clean, and you get this thread and rod. This gun actually generates this welding between the two so that you can attach another element onto it. That's pretty helpful for several types of connections, such as this one. All right? So there are really a set of tools that can perform more or less whatever you want in terms of steel construction. Now let's talk about the residential steel framing, because I know that these parts of the lectures are not very entertaining, but they're also somehow important. I'm trying to do them as entertaining as I can, but I know that there is an intrinsic limit just in showing things. Well, let's have a look at a couple of pictures, probably it would be easier. So what I want to show you with this image is that steel framing is very similar to timber framing in some ways. So what you see here are all the elements that we spoke about last week. So for instance, the steel stud, noggins, then you see here, this is a lintel, and then we see some trusses here, they are laying on the roof. We have some openings, so there is a jam stab and seal trimmer, so all the elements are actually there, all right? This is a wall track, the bottom track, top track, all right? So all the same elements. And there are a few differences though. So the elements need to be connected, like interlocked together. So in theory, the stud has to be slightly smaller than the track. And also the connections, you see, they've got these slots. So you don't use nails, but you use these slots because the wall tracks can deform, again, due to bending moment. And this slight deformation has to be taken in account by that connection. So this slot actually allows this track to bend, take this type of shape, and translate. Okay, so there is a release. Remember that, it's very important. All right? And this is another type of interesting detail. So this is the gem. When you've got a window, you double up the section. So you see here, this way or this other way. And so these are trusses. You see another lintel there, just showing you the elements, how they are, just showing you the similarities. This is the correspondent of noggins, just to reduce the height of the studs so that they don't tend to buckle anymore. And there are a couple of systems which are more interesting that generally are not, you won't do that with timber. This open web steel joist. Well, again, open web, again, it means that we get rid of the web and we transform it into a truss system. So what happens is that this is suitable for a lot of applications, generally when we want to, instead of a ground slab, but also for the upper floors. For the ground slab, the main advantage is that this is termite resistant, so we don't need to care about animals and these type of things. But also, look at this situation. Maybe we want to, there is all this mag and stuff, so we adjust our stamps. There is an adjustable height, so there is a rod we can, tight and adjust the height of that, and we place this open web steel joist just to clean up the site. Try to imagine to pour a slab on ground in that condition. So in this case, slopes, mag, this type of condition can be just avoided because you have these stamps, and then instead of the conventional steel deck, timber deck, you use these open web steel joists to make a flat and clean surface to work on and build the house. So that's one possibility. And as usual, there are all the pieces, all the standard pieces that allow you to make corners and all the types of connections, which are generally bolted. So all the connections you see here with these open web steel joists are made through bolts. I won't go any further because we have a lot of things to talk about, but an advantage is that generally you have room for services and air ducts. So this is one of the main advantages. Of course, you can drill a hole through steel and timber, generally in the neutral axis, but in this case, you already have room for that, so why use the other system? It's like a Posistrat. It gives space for this type of services. Look at the connections here. So these are just screws for the bars of the truss. They are only subject to axial forces, so there is no bending in a truss system, remember that. The same system applies to roofs. And now I'd like to talk a little bit about Bondek. So what is Bondek? You remember that in the lecture about concrete we spoke about lost formworks. Well, Bondek is one of these lost formworks. So what we do, we have this corrugated sheet of steel that is placed underneath. So that's the place where there is tensional forces due to bending. So that's where we want steel. We use it as a formwork to pour concrete. There is still a reinforcing mesh because concrete tends to shrink. So we use that also in the upper part to avoid and control shrinkage. And if we want to transfer shear forces between beam and slab, what we do, we use these shear connectors that, again, they clamp the Bondek system to the beam. Well, Bondek is broadly used to identify the construction technique, but is a trade name. So it refers to a specific brand. There are several systems which are similar, and generally we all refer to Bondek, but also Condek, Kingflow. They're all the same construction technique, just different trade names, all right? So just bear these in mind, just showing you a few examples. And here you see images of these shear connectors, and when the concrete is poured, But I'd like to show you also, if you look into the Bondek catalog, you'll find a lot of nice details and examples. Again, you see this corrugated profile is completely lost. When the concrete is poor, then the two elements combine together, participate together to resist to the force, tensional forces. They also have the same thermal coefficient, so they expand and contract in the same way. You remember we said that. And again, this mesh in the upper part, you wonder why, but it's mainly to avoid shrinkage. So it's not for any other specific reason. In this bottom part of the profile, they can also be used, you know, this profile here can be used to hang the hangers for the suspended ceilings. So that's used for that. And just a few schemes, you probably know that. Temporary props with diagonal bracing while pouring concrete, because of course the sheet is not able to resist the forces yet, you know, until it's cured. And what happens in this case, when you have a beam, you know, in the middle, so that the span is not free, you change the system. So in this case, you have a diagram of moment that becomes negatives here, then there is another peak here, and then it becomes positive again and negative. So the type of deformation you get is a little bit like this, you know, red line that I was drafting on this line. So what happens, the reason of these steel bars in the upper parts here and there is because of the, you know, the sign of moment changes. So it becomes from positive to negative because you're changing the constraints of the system, right? Of course, with Bondek you also get all the products to refine edges and corners. They're all commercial products. And I want to show you the images of that. So you see here the edge, how to make the edge. This one is the galvanized steel. That is the primary structure that supports the Bondek. And you see here from the bottom, what you see is actually just a corrugated profile, so you won't see the concrete. And to that, you generally suspend a ceiling. All right? Just very briefly, 2 minutes, and then we'll have a break. This building by McBride Charles Ryan is done out of steel, and also the cladding is with steel panels. So we need to speak about a couple of more members before having a break. So purlins and girts. Purlins and girts, generally they've got two different shapes, Z and C. And there are advantages and disadvantages I'll show you in a minute. Generally, Z sections can be overlapped to create joints, and the C ones, they can't, but they work very well for flush connections. So what happens here is that we've got a primary structure, okay, a skeleton done out of steel, and then we want to place a cladding on it. Cladding is generally manufactured out of panels. So there are panels of a specific size, and these specific panels, they need, you know, they need some rails to be able to be connected to the building. So what happens is that we have these girts on walls and purlins on roofs. The same thing, two different names. Purlins for roofs and girts for walls. It's like joists and rafters. The same thing, same principle, but one is for roofs and the other one is for floors. So what happens here is that we've got this primary structure and we want a flush cladding. So that's the way to attach the girth to the column. And in this case, we have got the bypass. So it just goes through because we attach it to the front. And therefore, the cladding, we need to consider an extra thickness on that wall. I mean, corners work in the same way. We just need to make sure we create an L for the bypass. We can also have details for the flush connection and also kind of semi-flush. But I mean, I'm not going into details. When you find an occasion in your own project of this type, then you just look into the detail. I just want to provide you the database of details so that you have all this material in the lectures. Roof purlins, you see here that when you get the Z profile, look here how easy the connection is, because they can just be overlapped and bolted. In the case of a C-section, that can happen. You need an extra plate, and you connect them this way, all right? But again, these are things that generally an engineer manages for you. And you can design very complicated shapes out of it, like this building you saw before in the cover. It generally, again, all the framing is done out of steel, but also the complicated facade, which is all faceted, is done in the same way. So I'm not going through that, but you see bonders, studs, noggins, jambs, all the elements are there, all comes together also with steel. Temporary props, probably they are pouring concrete. And here you see the primary beams, and then you see the girts or the purlins. So you see again primary members and secondary members, that they're ready to get, you know, the panels, the cladding panels onto that. And unfortunately, I don't have photos of the stage in the middle, but you see these panels are actually attached to that skeleton. And the way you define the spacing between that is according to the size of the panels. Unfortunately, last week it was a bit easier with the Melbourne Museum. There were photographs of everything. In this case, you need to trust me a little bit more. But you probably see here a little bit the structure, how it goes, and how to attach the panels from the top. So that's more or less the first part about steel, and we'll talk a little bit about steel architecture in the second part. Give it 10 minutes, so now this is 12:03. We'll start again at 12:13. And if you have any questions so far? No? Then I'll see you in 10 minutes. So are we all back? Ready to go? Well, the beginning of iron construction, steel construction, was this with this cast iron. And there is a very good example in Paris. I think that probably about 80 of these entrances of metro stations have survived. Some others have been reconstructed. But they are belonging to the period of the Art Nouveau, the Liberty. And so you see, these are the two different types you'll find in Paris. Well, in that period they used steel just in the shape of, you know, referring to flowers and other organic shapes, so that the idea wasn't really to standardize pieces and connect them together like we see nowadays in skyscraper and structural elements. But again, as far as I can see, there is no welding, there are other types of connections, and that was the beginning. There are also much bigger constructions, such as the Eiffel Tower, or there is a huge bridge in Oporto in Portugal. These are examples of the beginning of the birth of this new material, which is a bit parallel to the birth of concrete. So this is the beginning also of engineering as a discipline that separates from architecture. But what I like to talk about is mainly the modern movement. So what happens is that Mies van der Rohe is the key architect who actually played a fundamental role of generating, inventing the minimalism. So minimalism is the idea of using the minimum amount of material to express architecture. So the minimum possible also decoration, like Adolf Loos was before that trying to avoid all possible decorations and ornaments. So architecture should be expressed through the basic materials. And Mies van der Rohe found in steel a way to do so. So what happens in this case? You probably know the Farnsworth House. This is very close to Chicago, probably 50 miles away from that. And this case here, you see that there is, the house doesn't touch the ground. So we use steel again to just lift it up and have a clean flat slab. The structural columns, we could say universal columns almost, they're all exposed outside and connected. You see here a detail, so they're all exposed and connected to the window framing, but also they just go down straight to the ground. And an interesting part is that even with this podium, in this case, of course, there is a plate that welds this stump just to cover it. And everything is controlled precisely. So the idea of welding elements is so precise that you see them, you recognize them as a whole. So you see there is a control of all the operations, that you don't see bolts sticking out here and there. Everything is reduced to the minimum. So welding, all these type of hollow sections are actually covered with another plate to make sure you feel the solid material. Then it's painted white, and everything, the structure becomes the architectural part of it. Another interesting example, this is probably most interesting, more interesting in terms of steel, the National Gallery in Berlin. We've got a very wide span, and there is a waffle structure for the roof, but what the issue is that we want to get the minimum amount of supports. So look at this, 2, 4, 6, 8 columns on the 4 sides, and apparently they have been custom made. So this column, which is also tapered, slightly tapered, you see here, it's like a white flange, but like 4 white flanges, like welded together, like separated and re-welded together. So it's a custom made piece that takes advantage of the standards, but to make a new profile. And you also try to taper it, because of course you won't need the same amount of material towards the top. So this is the key. So designing with steel also means to do that. And what happens in this case, the connection between roof and column is done in a very elegant way. So we're not talking about welding, we're not talking about bolting. We just want the roof to sit of an element, you know, that doesn't allow translation. So we've got this extra piece here that again shows the separation between the two things, which are able to expand and move separately. So this is really showing how was the early exploration about designing with steel, using standard products, but also trying to find new standards, at least a standard that you can replicate throughout the project. Another example is the Crown Hall in Chicago. This is the School of Architecture of Chicago. It's the IIT. In this case, the standard is the portal frame. You see the portal frame here. So this one is the second one. And then there are other lateral elements to stabilize it. So what happens, architecturally speaking, we talk about the industrial use of that, because portal frames are used first in the turbine fabric in Berlin by Andries Petrus Berlage. So that's the idea of repetition of standard elements, because between this portal bay, this portal frame and the second one, we get a bay. So this is the architectural bay we replicate throughout the process, like in the old Gothic churches. Again, no bolts, these are all rigid connections. You see very clean and nice welds. So everything clean and nice. And if we look at the detail here, so you see this is the column of the portal frame, and then there are smaller ones that just make the rhythm of the facade and to which the frames of the windows are attached. So that's the way everything is expressed. So the steel is also creating the rhythm of the facade. The structure is exposed. I mean, there are several problems in these projects. In terms, for instance, waterproofing is not the best, so don't look at these projects if you really want to make a waterproof house. There are other problems related to protection of steel and fire, but we're talking about the development of minimalism here. And Mies van der Rohe went even further with that. And really the key points, the key projects in which steel is even used in a fake way, so without even a structural meaning, is in the Lakeshore Drive apartments, again in Chicago. That's in the north part of Chicago. So it is a safe neighborhood of Chicago. So yeah, what happens here? I show you straight away. Look at this. You see some columns here. Before mounting this panel, so you see that there is a column here and a column there, which is going to be covered by another panel, but in front of that there is a fake column. And why that? Because on the facade you still want to express that same rhythm, and also you want to express that your architecture is actually the skeleton, and all the other things are just glass. So there is nothing else than the skeleton and the glass. And in order to do that, considering this column was sitting inside because it was connected to the slab, it needs to replicate that outside just to emphasize the presence of that element. So that's what happens. The other ones, they are fine because they are the frames, they support the frames, but in this case, this is the structural column protected also by concrete, and then the fake one. So that doesn't do anything else than creating the rhythm on the facade. All right? So that's, if you want, this is the extreme use of steel in minimalism, which has been, it has been pretty diffused worldwide. Even if you go, like in my hometown, there is this the RAI skyscraper. So RAI is the national broadcasting company for TVs, like SBS. And this is the skyscraper they got in 1962. And what they did, there is a steel structure inside, but what they did outside the glass facade, they decided to replicate another steel structure to give an understanding of what happens inside. So the idea of minimalism is also that you need to read the structure. So everything is visible, readable, understandable. There are no layers, so there is no inside structural elements, protection, insulation, and cladding. Everything is visible. So steel and glass, everything is there. You need to understand what happens. We could also say it's honest. In architecture, these type of terms will come in the history classes, but I'm more interested in the lightweight structures. So there was a very important Russian engineer, Shukov. He actually designed the first steel grid shell in the world, but also a lot of masts and towers, and this became a symbol for Russia. They're thinking about demolishing that, but exactly I don't know why. This is a very important piece of heritage. And what's that? That's actually just a combination, a composition of catenoids. A catenoid is this shape here, the one you see here on the left. So it's just a catenary. So a catenary is a specific type of arch. And then the surface of revolution is the catenoid. So this one. What's the characteristic of that? Is that you can construct it out of a ruled surface. So you take sticks like that, straight elements of steel, you rotate about an axis, and you get a catenoid. You see here, these lines, they are straight elements of steel. Then you compose these catenoids, one on top of the other, you scale them down, and that's the tower. So that's a symbol for us. It's very lightweight. So that's a very efficient way to use steel. We'll talk in week 10 or 9, now I don't remember, lecture about shells and grid shells, what a catenoid is and what form resistant means. So we'll talk about that specifically, but this is just to show you that the use of these standard profiles can get whatever shape you want, all right? And you can push it even further. So steel is not only for this type of strong members, can also be used for cables. So in this case we are at the Olympic Games in Munich, 1972. So Fry Otto Melli, with another group of engineers at the Institute for Lightweight Structures, which is actually in Stuttgart, very close to that, they decided to design these roofs. So they are tensile structures, but also there are cable beams and struts. But all this is done out of steel, again, in a way that you can design that through fabric models, soft bubble models, to get exactly the shape in which you get only in-plane stresses, and that is called membrane action. We speak about that again in the lecture about shells and grid shells. What matters here is that this is done out of steel, and steel is a fundamental material for these type of structures. But it's also fundamental materials for domes, biospheres, geodesic domes, grid shells. So in this case, we are talking about the Expo in Montreal. So that's the Biosphere by Buckminster Fuller. Fuller, you definitely know this name. And what's interesting here is that when you got all these bars, so this is like, let me simplify it in this way. It's like a three-dimensional truss. So it's a spatial structure, like a truss made of elements going in three different directions, and then also deformed to get the sphere. So you know that the sphere can be discretized in triangles, hexagons, pentagons. And what Fuller does is exactly that, to discretize the sphere in a set of hexagons. You see them here, but then they are also like extruded in other elements to create the joints and to give a bit of thickness to that structure. And this also was the beginning for the development of the mirror joint, M-E-R-O. So that's just a kind of ball with 14 different holes to which you can attach steel bars at different angles. So that's the mirror joint. The mirror joint allows you to connect, as far as I remember, up to 14 bars, you know? So it's a huge amount of connections in one single node. And that's what happens with steel. That's also one advantage. But what we mainly talk about in the lecture of grid shells and shells is steel in this very lightweight form, like in the Great Court of the British Museum. So here we've got more than 1,000 different pieces which are bolted and welded together, partly off-site and partly on-site, but the form of this roof is done in such a way that, again, there is only membrane action. So this is a shell. It's, there is no bending moment at all, and everything happens in plane, so only in plane stress. So it's very lightweight. And this is all triangulated because with triangles, the glass panels are planes. If we have squares or quads, they can be doubly curved, so the glass would be very expensive. So they're all triangulated. And I'll explain you in that lecture how to do that a little bit, or at least what that means. And again, so this type of steel constructions really span from the very heavy one of the Tour Eiffel or the entrances of the metro in Paris, or they can go to the minimalism. We're still using standard products, or we customize standard products. So we refer to the market to get the specific design, or we can even think about something completely different, so form and structure, so lightweight construction. So steel is suitable for that. So these are the different possibilities. And a couple of notes, I think I'll just conclude here. Next week, the lecture is divided in two parts. There will be Blair Gardinet talking about site issues. He's the coordinator of construction design, so the subject you will take after construction analysis. And that's a specific lecture about how to treat the site and what are all the issues concerning the site before building the house. He will explain you in detail about that. The second part, Jeanette and myself will go through assignment 3. So how to animate your section, and more in specific, we'll prepare also a written document, you know, as you got for assignment 1 and 2. What to do, how to do it, when to do it. So we want to explain you what to do in the last 2-3 tutorials before the final submissions. So hopefully this will take 1 hour and 1 hour, and that's it. Okay? Thank you very much.